In this video, we're going to look at our third theory of acids and bases. Remember, we had Arrhenius theory and then Bronsted-Lowry, which is what we've spent most of our time on, and Lewis is our third one. So Lewis theory of acids and bases. And honestly, though we look at Bronsted-Lowry, Lewis is really what we're going to use mostly in this course. And if we think back to Bronsted-Lowry again, remember those were proton transfer reactions. So our acid is donating a proton, our base is accepting that proton. Lewis acids and bases are electron transfer reactions. So instead of transferring a positively charged particle, we're actually going to transfer a negatively charged particle, which means our acids are actually going to be the acceptors and our bases are going to be the donators. Everything's going to be completely opposite. So in the Lewis theory, these are electron transfer reactions. And our acid, our Lewis acid, is going to be an electron pair acceptor. And I am going to leave a little bit of space there because I'm going to come back and write something. And then our Lewis base is going to be an electron pair donator. So instead of, again, transferring protons like we did in Bronsted-Lowry, we're going to be transferring electrons. Instead of positively charged particles, it's a negatively charged particle. So what was the acceptor in one theory is now the donator in the other theory. So to donate an electron pair, the base first, it has to have an electron pair. So to identify a Lewis base, it's always going to have at least one lone pair of electrons. So must have at least one lone electron pair or non-bonding pair, whatever terminology you like better. Right? If it's going to donate electrons, it has to have electrons to donate, right? It has to have an electron source. In this case, that source is going to be a lone pair. Our Lewis acid, however, just has to have a place to put them. So I no longer have to have a proton, right? For a Bronsted-Lowry, if it's going to donate H+, I have to have an H, right? I have to have a hydrogen to be able to donate it. Here, I don't have to have a hydrogen anymore. I'm going to do an example of something that's an acid using our Lewis theory that would not be an acid using our Bronsted-Lowry theory in a minute. So what I have to have is a place to put those electrons. And what that's going to be is a relatively low energy empty orbital. So must have a low energy empty. Remember, electrons go in orbitals, so I need to have an orbital that has room for those electrons. So must have a low energy empty orbital or a polar bond to hydrogen. Because if I have that, when we break that bond, I have an empty orbital. And I can show you that also. So our first example, BF3. BF3 is a Lewis acid. There's no way it could be a Bronsted-Lowry acid because I don't have an H, right? If it's going to donate H+, right, donate my proton, I have to have a proton to donate, and this doesn't. So it's not a Bronsted-Lowry acid, but it is a Lewis acid. And that's not really all that obvious until we draw it out. So if I was to draw the Lewis structure for this one, I actually just have these three bonds. Boron is one of those atoms that is fine without an octet. I do have three lone pairs in each of those fluorine, which I'm not going to draw. I'm not putting a formal charge on them, so we know that it's there, which means this boron here is sp2 hybridized. Right? It has three electron groups. Three electron groups are sp2 hybridized. So what that means for us, remember if something's sp2, it's going to have three sp2 orbitals, but it also has one p orbital. So if I was to draw my orbital bonding picture for this, the 3 sp2 orbitals are going to be overlapping with the sp3 orbital of fluorine, right? There are 3 lone pairs on those fluorines, so they're sp3 hybridized. And then the p orbital is on there. Remember, our p orbitals are perpendicular. So I could kind of shade this one, showing that it's coming out at us. Let's do a little bit better job there. So I have a p orbital, and then the other side I could dot. I'm gonna get this. So I do have this empty p orbital on there. Because I have this empty orbital, I can put electrons into it, meaning it's a Lewis acid, right? A Lewis acid must have, highlighter, must have a low energy empty orbital. Here we go, empty orbital. So because of that, it makes it a Lewis acid, right? This can accept electrons. We're gonna get this. Sorry, can accept electrons. This must be painful to watch. So draw it out. It's sp2 hybridized. There's an empty p orbital. It can accept electrons. The polar bond part, if I was to have hydrogen bonded to chlorine, and this is kind of Bronsted-Lowry thinking, right? If this was to lose the proton, right? If I was to put it in water and it's to separate, if you want to think about Arrhenius theory, right? It's ionizing, however you want to think about it, this is an empty orbital. So if the bond is polar, it's easy to break, which means we're just going to kind of assume that we can. Once it breaks, the orbital is empty. Remember hydrogen, I have my nucleus with a proton in it. Most common isotope has no neutrons, a totally not even close to scale electron cloud. And I would have an electron sitting there if it was uncharged. As soon as it's charged, right, we're losing that electron. And that orbital is now empty. So H plus has an empty s orbital, right? There's no electrons in it. So if I have a polar bond to hydrogen, that bond is easy to break, leaving me with this empty orbital. So our Lewis acids will always have some sort of empty orbital or a way to make an empty orbital pretty quickly. My Lewis bases will always have at least one lone pair of electrons because to donate them, we have to have electrons to donate. Incidentally, all Lewis bases are Bronsted-Lowry bases. LB for Lewis base. Let me go put those abbreviations up here because I'm going to use them a lot. LB, LA. So all Lewis bases are also Bronsted-Lowry bases. That's not true for acids. Remember that BF3 example we just did is a Lewis acid, but it is not a Bronsted-Lowry acid. But all Lewis bases are. Remember Lewis bases, and we'll just draw ammonia here. Lewis bases are going to accept a proton, right? So if this is going to act like a Lewis base, it's going to react with an acid, and we're going to form this. Right? Those electrons in that bond that I just drew are those electrons. Remember my acid, the part that it's taking is H plus. It might be easier to think about that and just kind of ignore that. It's taking H plus. H plus is adding to it, right? If we're thinking Bronsted-Lowry, it's going to accept that H plus. That H plus has no electrons, right? We just drew that picture up here. There's no electrons. Remember, bonds are electrons. In chemical reactions, we're forming bonds, breaking bonds. It's all about the electrons. So if a molecule is going to accept right? If a molecule is going to bond to a particle that has no electrons, it better have electrons, right? The only way a base can accept a proton is if that base has a lone pair. So all Bronsted-Lowry bases are also going to have that lone pair. They can't bond to H plus if they don't have something to bond to it with. So Bronsted-Lowry bases also have a lone pair of electrons on them. So in this section, we are going to draw arrows showing that electron movement. So we're going to take the curved arrows that we did in resonance, right? They always go from the source to the receptor, and we're going to apply it to our first reaction. So if I draw out my BF3, right, it has an empty orbital on it, and water is going to be my base. And what I'm going to form, and it's going to look kind of weird. Oop, that makes no sense. That should be a fluorine. Looks even weirder if I start introducing atoms we don't have. Just drawing my geometry too. And then there is a formal positive charge on this oxygen, and then there's a negative charge on that boron if you do your formal charge calculation. So what we're going to do is we're going to draw the curved arrows showing how we get from reactants to products. So just like we did with resonance, our curved arrows show where our electron movement, but they always go from the source to the receptor. They're showing the electrons are grabbing onto something. So what we're doing is we're forming this new bond, right? In my reactants, I didn't have a bond between oxygen and boron. In my products, I do. I had 2 lone pairs of my oxygen on my reactant side. I only have 1 lone pair on my products. Sorry, on oxygen on the reactant side. Only 1 lone pair on the product side. Sorry if I said that in an incredibly confusing way. So the arrow is going to go from one of those lone pairs. It's going to bond onto that boron. And that's it. That's my whole entire arrow. So those electrons that I highlighted over on my product side, we'll re-highlight it so you can see what I'm doing, right? These electrons right here are essentially those electrons. They went and they grabbed onto that boron and we formed a bond. So our curved arrow showing electron movement. One of the reactions that we did when we were talking about Bronsted-Lowry acids and bases was this one. So I had this alkene, or alkyne, so carbon with a triple bond. Again, don't worry about the name of it. We're going to do that in chapter 3. And then it reacted with nitrogen, the lone pair, 2 lone pairs, 2 hydrogen, negative formal charge. And then we ended up with this as my products. So we're going to add the curved arrows to this. So how are we getting from point A to point B? What's grabbing onto what? So again, the easiest way is to just kind of analyze the before and after. This nitrogen has 2 hydrogen on this side. It has 3 hydrogen on my product side. On my reactant side, it has 2 lone pairs. On my product side, it only has 1. So one of those lone pairs grabbed onto a hydrogen. If I look at this, that carbon on the right has a hydrogen bonded to it. On the product side, the carbon on the right does not have a hydrogen bonded to it. So what's happening is one of the lone pairs from nitrogen is grabbing on to that proton. Then the electrons, right, between that proton and the carbon are going to go on to carbon, right? Carbon over here has a lone pair on it. So those arrows. And it doesn't matter which lone pair you take. You can take either one, but it's going to grab onto that hydrogen. I'm not done because we then need to break the bond between hydrogen and carbon. Otherwise, I would end up with this thing, which would be wrong in so many different ways. right? Remember, hydrogen can only ever have one bond or two electrons, and here it has four, and that's completely not possible, right? It only has an s orbital. There's only one s orbital per shell. Each orbital can only hold two electrons. Hydrogen cannot have four, so we cannot do that. So anytime you form a bond to hydrogen, if hydrogen already has a bond, you are fully committed to breaking a bond. So as soon as I grab onto hydrogen, I need to break a bond from hydrogen. And that's always going to be true. If you're taking a proton that's bonded to something already, then you need to break that bond between what it's bonded to and it, right? Every time you grab a hydrogen, you're fully committed to breaking a bond. That second arrow has to be there. And those are all of them, right? If I look, get the highlighter out, this new hydrogen that's bonded to that comes from those electrons, is grabbing onto that hydrogen. And then we broke that bond. Those lone pairs are these lone pairs over here on carbon. Let's do one more. So sulfur-containing compound, and then we'll react it with acetic acid. Let's actually draw that proton out. And we have a conjugate acid plus my conjugate base. Which direction is forwarded on this one? Or favored. Sorry, not forwarded. I think I just gave you the answer. The forward direction is favored, right? This has resonance, this does not. So my conjugate base that has resonance is more stable and more likely to form, right? My electrons are delocalized. So again, kind of comparing before and after. The acetic acid molecule on this side, right, it has a proton. Its conjugate base, acetate over here, does not, so it lost the proton. Here sulfur doesn't have one, here it does. So one of those lone pairs on sulfur is going to grab onto that proton, and then again, as soon as you grab onto that proton, you are fully committed to breaking a bond from that proton. So one of these lone pairs is going to grab onto the hydrogen, right? And just the hydrogen, not the electrons. And those electrons are going to go onto oxygen. Now be careful when you draw these too. You want to draw them where they're going and where they're coming from, right? Like this arrow here, making it thick, it's those electrons in the bond, so I'm starting at that bond, right? Here I'm pointing at that hydrogen because that's where we're going. It's not just going to go off into space. This part is going onto that oxygen because that's where that lone pair is going. It had two lone pairs. On my product side, it has three. So just be really careful that your arrows are coming from where the electrons are, and they're going to where the electrons are going. So those would be my curved arrows for that one. So two new terms that I want to introduce also in this video are electrophile and nucleophile. And these are going to come up again, and we'll use them quite a bit, but now is a really good time to introduce them. So an electrophile, abbreviated a capital E, sometimes a capital E with a positive charge. And our electrophile is going to be an electron poor site. So it actually doesn't have enough electrons, it wants electrons. So it is our electron poor site. Electrophile, if you were to kind of translate that word, it means it loves electrons. If you see that word phile, it really loves it, it likes it a lot. So this really loves electrons because it's short on electrons. So this is my electron poor site. And Lewis acids are actually electrophiles. This is my electron receptor. If you think electron receptor, electron source, this is the one that's deficient in electrons. It's my electron receptor, my electron poor site. Nucleophile, capital N, lowercase u, sometimes a capital N, lowercase u with a negative sign. Nucleophiles don't always have to be negatively charged. Same with electrophiles. They don't always have to be positively charged. They could be partial positive. But this is my electron-rich site. It loves nuclei because nuclei are positive, and this guy is negative or has extra electron density. So my electron-rich site. Lewis bases are nucleophiles. They have those lone pairs, so they're electron-rich. Those curved arrows, whenever we're drawing them between different structures, it always goes from our nucleophile, our electron-rich site, to our electrophile, our electron-poor site. So our curved arrows go from the nucleophile to the electrophile, right? From our electron source, right, our electron-rich site, to our electron receptor, our electron-poor site. So I got this guy, and then this one, and this is going to be my nucleophile. It has my lone pair. This is my electrophile. That carbon in the center with the positive charge is not octet, so it is electron poor. And if I was to add my arrows for this, it's going to go from my nucleophile to my electrophile. So that's grabbing onto this. Because that carbon with the positive charge is sp2 hybridized, right, it does have an empty p orbital. So it is a Lewis acid, right? There's an empty orbital that can accept electrons. And then if I draw my product, it's going to look kind of weird because I didn't break a bond, I only formed a bond. So that oxygen is bonded to that carbon, and then that carbon still has a hydrogen. It still has the two CH3 groups. And then that oxygen has a lone pair, and then it also has, it's like half skeletal and half not. Sorry for this crazy mix of structures. If you wanted to write these ones out, it would be CH2, CH3 on each side, if that's easier. That does look kind of weird. It might be better to write CH2, CH3 for each one of those, but we do get that bond between them. I still have a formal charge on this oxygen now. My net charge on both sides should always be the same. Going back up to the examples we already did, we could label the electrophiles and nucleophiles if we wanted, which I want to do. So my nucleophile, right, my electrophile. My arrows always went from the nucleophile to my electrophile, right, from electron-rich to electron-poor, nucleophile, and electrophile. Right, nucleophile is my electron-rich site, electrophile, my electron-poor site. Our curved arrows always go from the nucleophile to our electrophile.